Okay. Oh. Okay, so we talked about what's an ionic bond, what's a covalent bond, but in truth, this is kind of under that heading of, hey, we've been lying to you all along. Oops. We've been saying, and you learned in physical science, there are ionic bonds, there are covalent bonds. It's that simple. It's not that simple. Nothing's that simple. It's not cut and dried. Okay, so it's a continuum, and we talked a little bit about what a continuum is. We have continuums of color, continuums of personality, continuums of all kinds of things. So you remember our old friend electronegativity, which is how strongly it attracts the electron cloud, how strongly it pulls the electron cloud. And I believe we had drawn that with ammonium, where nitrogen is going to suck up a lot more of that electron cloud than hydrogen is. So it's going to end up looking basically funny. That's okay. Oops. Okay, so every single atom on the periodic table has an assigned electronegativity. There's a number. So this is like height or weight or whatever. Well, no, it's not like any of those things. It doesn't change. It can't change. So all the elements on the periodic table have an assigned electronegativity. And those electronegativities go from like 0.1 something, you know, whoops, wrong color. You know, let's just say 0 to 4, okay? The maximum electronegativity is 4. Oh, actually, I know what the minimum is. Duh. It's 0.7. The lowest electronegativity of any element, 0.7. So the maximum difference you can have in electronegativity is 3.3. If you take the most electronegative thing there is and the least electronegative thing there is, then you have a difference of 3.3. And that means that they are total, there's no sharing going on whatsoever. This is me, and who here likes oatmeal raisin cookies? Okay, this is me and Katie and a plate of oatmeal raisin cookies. Set it on the table between the two of us. There's no sharing going on. She gets them all. All hers, thank you. There is no sharing. We have a maximum difference of electro-raisin cookie activity. Okay? When two things are identical in their electronegativity, and there's 0 difference, like identical twins who feel exactly the same way about everything, there is no difference in how attracted these electrons, these atoms are to the electron cloud. They have to share that evenly. There's no choice. So that's a difference of 0. That happens when you have diatomic molecules. Nitrogen and nitrogen, hydrogen and hydrogen, oxygen and oxygen. Anything where you have two of the same molecule bonded together, they have the same electronegativity. There's no difference. They share it 100% evenly. So it's easiest to look at this, because we said it's a continuum, it's easiest, I think, to look at it on a scale like this. So this is difference in electronegativity. And we said the maximum difference is 3.3. Well, the minimum difference you can have a 0 difference. That's the absolute 0. There's no difference between these two things. And what we call the middle is the 1.7 mark, which is actually a little bit that way. Okay. So if you're anywhere from here to here, this is a covalent bond. From here up is an ionic bond. Now, remember how I said it's not as simple as I've been telling you all along? So the challenge comes in that there are two kinds of covalent bonds. There are covalent bonds where they are being shared totally evenly. So they're purely covalent. That's things like, H2, N2, O2. And then there are things where they're not quite shared evenly. So the cutoff mark here is 0.3. So if we're between, let me shrink this little arrow. If we're between 0.3 and 1.7, this is what's called a polar covalent. And if we're between 0 and 0.3, this is a non-polar covalent bond. So in this one chart, we have sort of three bond types. It's really two bond types, and one of those has some subcategories. You probably learned a little bit about polar and nonpolar bonds in physical science. It's kind of been nice for me to have some kids from physical science coming in for tutoring, because I get to get a glimpse at what you should have had. So what are polar and nonpolar? Let's talk about this. Oops, do you have this? Okay, so now what we want to do is, number one, I want to talk to you. Does anybody here already know the difference between a nonpolar covalent and a polar covalent bond? Because my guess is no, and that's fine. So I want to talk a little bit more about what the difference is between them, because you all understand the difference between an ionic and a covalent bond. You get that. That's easy. So let's talk about what polar and nonpolar covalent means. Okay, so the first thing to know about a nonpolar bond, electrons are shared evenly. Well, why do we call it nonpolar? It's going to be easier to explain that once we look at what a polar bond is. So a polar bond, obviously electrons are not shared evenly. Okay, so the electron cloud is really what we're talking about here. In one of these, if we use the sort of tugging the blankets off you in the middle of the night metaphor, in a nonpolar bond, everybody's covered by the same amount of blanket, the same amount of electron cloud. In a polar bond, one atom is pulling the electron cloud over onto itself. So in a nonpolar bond, and let's just look at H2, we have hydrogen and hydrogen. They're sharing two electrons. And their electron cloud is evenly distributed. Neither one of them is able to pull it differentially. So if we remember that those little electrons could be anywhere in that electron cloud, there's no one area of that molecule where there's a concentration of positive or negative charge. Okay? Because the nucleus of each of these is positive, we know that. Let's change colors on that. Now we have a positive nucleus in each of these, and those little electrons could be buzzing around anywhere. So there's no defined region of charge. The electron cloud is distributed evenly, there is no region of charge. Let's look at everybody's favorite polar molecule. You all know it. You all love it. You've all drunk it. Water. Yeah. So we have, we're talking about water, we have an oxygen, we have two hydrogens. And, never mind the fact that oxygen has some, well, we won't even talk about that yet. So look at that table of electronegativities. What's the electronegativity for oxygen? Okay, so oxygen has an En, En for oxygen is 3.5. What's the electronegativity for hydrogen? 2.1. So what's the difference here? 1.4 is the difference in electronegativity. If we go back and look here, that places the oxygen-hydrogen bond someplace way up here. It's very polar. It's almost ionic. Oxygen really loves the electrons. Hydrogen, whatever. You can have mine. You can have them. So when we have the electron cloud around this molecule, what we see is that the electron cloud gets pulled in really tight around those hydrogens, and most of it actually ends up down around oxygen. Well, what's left when you pull the electrons off of hydrogen? A naked proton. Not even neutrons. There are no neutrons in most hydrogen. It's just a proton. A naked proton. If you have small siblings or cousins, I threatened the year my daughter was 1 for Halloween that I was going to dress her up as a hydrogen ion, which is just a naked proton. So I was just going to put a plus sign on her belly and have her run up the street. My husband vetoed that. I thought it was hilarious. Nobody else would have gotten it. Naked child with a plus sign on their belly. But if you have small siblings, by all means, don't do it yourselves. You're too old. It's illegal at your age. So when we pull all those electrons off of hydrogen, those are just naked protons, just hanging out there in space. So that entire end of the molecule ends up having a positive charge. Well, down here, this is all electron cloud. So what kind of charge would that have? That has a negative charge. So down here, you have a negative charge. What you now have is a molecule that has distinct poles, like the north and south pole of the planet, or the poles of a magnet. This has regions on each end of opposite charge. And polar molecules do all kinds of interesting things. They line up in particular ways, just like magnets will, because they've got these regions of charge. So when they start to interact, all the little positives line up by all the little negatives. So they do some weird stuff. And water definitely does some weird stuff. So in a polar molecule, the electron cloud is not evenly distributed. And there are regions. We call it partial charge. Regions of partial charge. I know, it's really hard to read that. Let me see if I can fix it. Okay. Yes, ma'am. Yeah. Yeah, so there are regions of partial charge on a polar compound. So anything that's falling in here that has a polar covalent bond is a polar compound. And things that are falling down at this low end are the nonpolar compounds. So they actually behave differently. When we get into solutions, we'll talk more about those. But they do have some interesting characteristics based on the fact that they are polar. Okay, questions on the difference between polar and nonpolar? I always feel like that doesn't get explained very well in physical science because you're kind of skimming the surface. So I want you to understand that well because it will become important later. But for right now, what you're going to do is just predict what kind of bond would form based on electronegativity differences. So using page 151 in your book, the table of En, I'm going to toss out a pair. You tell me whether it would be ionic, polar covalent, or nonpolar covalent. Okay, are you ready? Okay, magnesium and oxygen, go. Okay, what's the electronegativity for magnesium? Who's got it? Okay, so En of magnesium is 1.2. What's the electronegativity of oxygen? 3.5. I screwed up. I should have put that one down below. Electronegativity of oxygen is 3.5. What's the difference? 2.3 En difference. Okay. So, how many of you would say ionic? How many of you aren't quite there yet? You can be not quite there yet. Okay. Okay. So, who said? And I've got this written up here. Who says ionic? Everybody. Good. Yeah, that's an ionic bond because they have a 2.3 difference in electronegativity. So, how about carbon and oxygen? Okay, so oxygen has an En of 3.5. Who's got carbon? What is it? 2.5. What's their electronegativity difference? 1. What kind of bond are they going to form? They're going to form a polar covalent bond. So, do you know of any compounds that we talk about on a daily basis that are formed from carbon and oxygen? There are 2 that we talk about a lot. No, that's not what I'm thinking of. Gases in the environment. CO2. And what's the other one? So carbon dioxide and carbon monoxide, CO. And those are both, you now know, polar covalent compounds. Okay, let's do one more together and then I'll cut you loose. Nitrogen and oxygen. Notice that oxygen comes up a lot. Oxygen, oxygen, oxygen! Okay, nitrogen has an electronegativity of 3.0, right? And who's got oxygen? 3.5, again. Okay, so oxygen has an electronegativity of 3.5. What's the difference? 0.5. What kind of compound are they going to form? Polar covalent, but just by a hair. They're not terribly polar, so it's not got strong poles. It's a weak polar covalent compound. Whoops. Okay, so polar covalent bond. Okay, let's do one more. We'll do copper and chlorine. Okay, let's just skip the copper and the chlorine because something weird happened there. So, you now have homework. You can work on practicing these, and there are no weird ones like the one we just did. So, this is the chapter review for Chapter 6. And right now, I'm just assigning the ones that we've already covered, so you should be able to get these done. 2 through 4 and 33 and 34. So while you're doing that, I'll grade the tests, and I should have them to show to you at the end.